Hello everyone. I'm giving some series of lecture for the course Probability and Statistics, and we are in the joint probability distribution chapter, right? So in case of a single random variable, we have seen that the probability mass function, density function, all these things. Then after that we discuss about the expectation of the random variable, right? And the variance of the random variable. Now these things we'll discuss for the case of a joint probability distribution, right? So let us recall what we know it already. For a random variable x, the expectation of x is defined as e of x is equal to x px summation x px if x is discrete type, and it is integration x fx dx over minus infinity to infinity if x is continuous type. Then for any function h, we know that e of hx is equal to, just in place of x you have to put hx, and then it is same if it is discrete, and in place of x you have to put hx if it is continuous. So in particular, if you take x to the power n, it is a summation of x to the power n px, and it is integration x to the power n fx60. So these things already we know it, right? Now what will happen in case of a joint probability distribution? So the result is, for two random variable x and y, so expectation of xy is equal to summation over x summation over y x into y pxy, where pxy is what? It is a joint probability mass function of x and y if x and y are discrete type. And similarly, expectation of xy is equal to some integration minus infinity to infinity, integration minus infinity to infinity, x into y fx dy into dx dy. What is fxy? It is the joint probability density function of x and y whenever x and y are continuous time, right? So in this way we can define the expectation of x into y. And then we can also have that if hx and gx, h and g are two function, then the same thing will happen. In place of x and y you have to put hx and gy, hx and gy if x and y are discrete, and it is if x and y are continuous, right? The same thing, the one we have discussed earlier. Now we can solve some example. Now look at this example. In a study of responses times y versus the number of bursts of signal strength x of a particular network, the joint PMF is given in this table, right? You have to find the joint expectation of x and y. You have to find the joint expectation of x and y. So how to do it? Now this kind of example we have solved earlier also, right? So what are the things are given? It is this, in these terms are what? So this is what? This is P of 1 comma 4, right? Actually 4 comma 1 it is, because it is given in this way. Similarly, this is what? It is P of 4 comma 2. This way joint probability mass function is given, right? All the things. So what you have to do, we have to find the joint expectation of xy. So where x and y are, we understood it is a continuous type discrete random variable. It's a discrete type random variable. So what is the formula? We know that expectation formula is basically E of xy. It is what? Summation over x and summation over y. So y first we'll do. So y is what? From 1 to 4, because y have 4 values. And x is equal to what? X is equal to 1 to 3. Then x into y into this pxy. Now we have to do that, means how many terms we have to calculate this type of term. It is 4 is a 12 term we have to calculate. How? Suppose x is equal to 1, y equal to 1. So it is 1 into p of 1, 1. We have to calculate. Right. In this way, we have to do 12 terms. So instead of doing it individually, what we can do? We can make a table and then we can do it. Right. So we will do the table in the next page. Yes, somewhere here. what we'll do, we'll make a table. So what we can do, we can make a table like this, and this side we may make it as x is equal to I, this one, and y equal to j in this side, below side. And x values are 1, 2, and 3. X is equal to 1, 2, and 3. And y is equal to, there are 4 values. Y equal to what? 4, 3, 2, and 1. So this term is what we'll do. It is 1, right? 1, 4, 1. Y value is 4, x value is 1 into p of 1 comma 4, like that. So what will happen in this case? So 4 into 1 into 0.15, 4 into 1 into 0.15. What is that value? It is 4 times 1 into 0.15. So it is equal to 0.6. Right? The same way we can do the other things. It is, this value is what? 4 into 2. The second one, this value is 4 into 2, 8 into 0.10, 8 into 0.10. So this is what? 0.8. And similarly, we can finish the table. So 3 4s are 12 into 0.5. So it is 0.6. And in this way, we can finish the whole table. 0.06, 0.6, 0.45. Again, what about this one? 2 into 1 into this value, 0.04. Similarly, 4 into 0.this, so 0.12. We can finish the table, so that all the values we are doing it very systematically, and at the end we will just add them up. So 0.75. Done. Now what about this term, the summation of this? It is actually, if we just do sum over all the table, we can get the value. So basically, expectation of xy is equal to summation of y is equal to 1 to 4, summation of x is equal to 1 to 3, xy into pxy. But this value is actually, if I do, I have already calculated. This value is the sum of all the these values. This one, this one, this one. So this value, this value, this value, we have to add them up. Not this one. Right. So and if you just add them up, you can use the calculator. You will see the value is 5.27. So we have calculated the expectation of x and y, x into y. Right. So this one we have done it for the case of a discrete type random variable. Now we will do one example for continuous type also. So look at this example. The two random variable x and y have a joint density function given by fxy equal to 24xy. If 0 less than x less than 1, y value is also between this, and x plus y value is between 0 and 1 and equal to 0 otherwise. Find the expectation of x and x into y. Right? So how we can calculate? We know that again in case of a continuous type, the formula is e of xy. Now in this case it is an integration, right? Y is actually minus infinity to infinity, x is again minus infinity to infinity, then xy times fxy dx dy, right? So we have to find this integration. Now to do the integration, we all know that we need to understand the what is the region is given, right? So region of the integration is what? So we have to find this integration value, but let us first understand what is the region given. So the region is x is between 0 to 1, y is also between 0 to 1, and x plus y value is between 1. So this region is basically this region, right? X is equal to 0 to 1. So this is the, what are the vertices? This is 0 0, this is 1 0, this is 0 1, and what is this line? It is x plus y is equal to 1. So it is below that region. So our region of integration actually this one. Our region of integration is this part. So how we can do that integration? How to do it? Now to do this kind of integration, we have to first do the integration limit, right? So which integral you want to do first? So we all know, right, that how to find the integration limit for this cases. So what we'll do first, we'll do the x limit or y limit, anything is fine. We can do the x limit. What we'll do, so x limit if I do, then we have to do, so we want to do the integration first over y. So in that case, what we will do, we have to make a vertical strip, and you check where it is entering the this region. Somewhere here, at that point, what is the y value? At this point, y value is 0, and it is ending at what point? It is ending at this point. At that point, what is the y value? It is 1 minus x. Correct? So therefore, integration limit is, for y, it is, so e of xy is equal to, we'll do the integration first over x. So y value is basically 0 to 1 minus x, right? So y value, we got it like that. Then what is the x limit of integration? How we can calculate? So that is the multiple integral concept. So this kind of vertical strip, how, from where onwards we can start? I could have taken the vertical strip here also. I could have taken here. I could have taken here. But from where onward it could start? So the vertical strip, I should start from this line onwards. At that point, what is the x value? So the x value is actually between 0 to, and where, up to where you can, I could have taken the vertical line here also. I have to end it at here. I cannot go more than that. So at that point, the x value is 1. So x value is between 0 to 1. So in this way, we can calculate the limits of the integration. So we have learned these things in calculus. And after that, just we have to substitute the value, fxy value, and we can get it. So e of xy is first of all x into y, we have to put, into, we have 24 xy, that is the fxy value. And we are doing integration for y first, so it is y first and then dx. Right? Now it is very easy. So first we'll keep it for x is equal to 1, we'll keep reserve, and we'll do the integration over y. So x 24, I will take it out. X square also I am taking it out. And then integration over 0 to 1 minus x, y square dy I have. Y square dy value is what? Or maybe I'll write down one more line. It is y equal to 0 to 1 minus x, y square dy. And outside I have dx. Right? And then it is 24, 0 to 1, x value, x square times y cube by 3. And from 0 to 1 minus x dx. And we can simply do it 0 to 1. So 3 I will take it out. X squared times 1 minus x whole cube dx. And then we can do this integration as 8 into 0 to 1, x square into that. So x square minus 3x, so minus 3x cube plus 3x square, so plus 3x to the power 4 minus x to the power 5 dx. And if I do the integration, it is, and after putting the limit value, we'll be getting, this is 1 by 3 minus 3 by 4 plus 3 by 5 minus 1 by 6. Right? So 1 by 3 minus 1 by 6 plus That this. Okay. Now if you just simplify it, you'll be getting this value is 2 by 15. So we calculated the expectation of this. Right? So this is a continuous type. I hope you understand. Okay. Now I'll move to the next thing. Now we discuss about the concept of the expectation. Now if x and y are independent, what will happen in that case? The expectation of x and y, x into y, right? If x and y are independent, then expectation of xy is equal to expectation of x into expectation of y. So they are individual expectation product. And expectation of hx gy, for the case of independent random variable x and y, it is expectation of hx into expectation of gy. So if they are independent, we can just write them their separate individual expectation. Now we have discussed that expectation part. Then what about the variance of joint distribution of joint probability distribution function? Now in that case, we'll not say the variance, but we'll say that the covariance. Right? So what is that? The covariance between any two random variable x and y, it is denoted by cov xy, COV, covariance xy, and it is defined as cov xy is equal to expectation of x minus expectation of x into y minus expectation of y. So their product is the covariance of x and y. Right? So this is the definition of covariance. Now we know that variance calculation formula that E of x square minus EX square. So similarly, covariance, to calculate the covariance also we can have a formula, working formula. And this is also very easy to prove. How we can prove? So you assume that, or let A is equal to, because expectation is a constant term, so let A is that constant expectation of x, and B is the expectation of y. They are the constant term, right? And therefore, what is the definition? So the covariance of xy is equal to, according to the definition, it is x minus E of x into y minus E of y, which is B. This is by the definition. And then we can just simplify it. It is xy times ay minus bx plus a into b. But we know that expectation is linear type, so we can just separate them out. E of xy minus, this is the property of expectation, a into e of y minus b into e of x plus expectation of a constant term. We know that it is the value is the same, ab. Now this is what e of xy minus a into e of y is what? It is b, minus b into e of x is what? It is a, plus a into b. So therefore one term we can cancel, and this I can write it as e of xy minus a means what? It is expectation of x into b means what? Is expectation of y. So we got this formula. Covariance of x comma y is equal to expectation of xy minus ex into ey. I hope it is clear. Now again, if we have that x and y are independent, so we know that if x and y are independent, then expectation of xy is equal to expectation of x into expectation of y. Therefore, in that case, the covariance should be 0. If x and y are independent, then covariance of x comma y is equal to 0. But the converse is not true. It is not always true. That if covariance is equal to 0, that does not mean that x and y are independent. We'll have some example, we'll show you, right? So we understood that if x and y are independent, then their covariance is 0. But if their covariance is 0, that is not like necessarily x and y are independent. They may be independent, they may not be. We cannot give any guarantee. Okay, now let us do one example. The same example where we have already calculated the expectation of xy. We'll calculate the covariance of x and y for that. So we already calculated up to the expectation of xy. right? This part we have already done in the previous example. Now what we have to do, that to find the covariance xy, we need to find these things, a of xy minus ex into ey, the individual expectation we have to calculate, right? But to get the individual expectation, what do we need? What is the formula for expectation of some random variable? It is expectation of x is x into pxx. Pxx is what? Is the marginal probability mass function of x. Ey is what? Marginal probability mass function of y. So we need to first calculate pxx and pyy, marginal PMF of x and y. Now we know that from this table we can able to calculate the, because this is the PMF, joint PMF table, right? From there we can calculate the marginal also. How to do that? So maybe we'll show it once. So we have to first calculate the pxx. So x value is 1, 2 and 3, right? So px of 1, px of 1, how to calculate? That means it is sum over all y we have to do. Sum over all y. So p of x of 1, it is that to get that value we have to do sum over all y, then pxy, right? So marginal we can calculate in that way. So x value is 1 and y value is over sum over all y. So this is 0 0.15, 0 0.1, 0 0.02, 0 0.02, 0 0.1. So it is 0 0.15 plus 0 0.02 plus 0 0.02 plus 0 0.01. And this value is equal to 0 0.20. Right? In the same way, px of 2 is what? We have to do the sum over all these values. So what is the value? 0 0.25. It is 0 0.25. The same thing, px of 3 is what? Probability mass function at the point 3. Sum over all of them. What is this sum? So 0.3 plus 0.55 to 0 0.55. So we have calculated the probability mass function of x. Marginal probability mass function, we call it, right? And therefore expectation of x is what? Therefore the expectation of x is summation of x into px. So what is the x value? So 1 into px1 plus 2 into px2 plus 3 into px3, right? So 1 into 2, 0 0.20, 1 into 0 0.20 plus 2 into 0 0.25 plus 3 into 0 0.55. And then if you just simplify it, we'll be getting this value as 0 0.35. So then we have to calculate this one. So for that, we need the marginal PMF of y. So we can do it in the same way. In this case, probability mass function at for the case of a y equal to 4. For y equal to 4, how we'll do? Py of 4 is sum over all the x, right? So how, what is the sum? 0 0.15 plus 0 0.10 plus 0 0.05. So therefore, again, I should write it as Py of 4 is what? The sum over all of them, it is, if you calculate, it is 0 0.30, right? Sum over all of them, it is 0 0.30. Similarly, this value is what value? 0 0.17. So Py of 3 is equal to 0 0.17. At the same way, Py of 2 is what? If you calculate, you will be getting this value as 0 0.25, and Py of 1 is equal to P of y of 1 is 0 0.28. Right? So we get these values, all the value. If you calculate, you will be getting this value. And therefore, E of y is what? Expectation of y is 4 into Py of 4 plus 3 into Py of 3 plus 2 into Py of 2 and plus 1 into Py of 1. And if you put the value, you will be getting this answer as 2.49. Right? So therefore we got all these things. So we know that covariance of x and y, this formula is equal to expectation of xy minus ex into ey. But this value is 5.27 minus this value is we got it as 2.35 into 2.49, and we'll be getting this value is actually a negative quantity, which is minus of 0.5815. So the covariance between x and y is equal to minus of 0.5815. Okay. Yeah, so this one we have already done. Now we will do one example for the case of a continuous type random variable, right? Covariance between x and y. The same example we have already discussed about it. Now already we have calculated the e of xy. In the previous example, it is 2 by 15. Now what we need to calculate? We need to calculate that expectation of x and expectation of y. Right. So we know that expectation of x is what? It is expectation of x is equal to, it is the integration minus infinity to infinity x into that fxx dx. And what is this fxx? It is the marginal density function of x. Similarly, e of y is equal to y. So the marginal density function we need to calculate. It is minus infinity to infinity y into fyy of into dy. So both the cases we need to find this one and this one. Now how to calculate that fxx, the marginal PDF fxx? So fxx value is for the case of x, the x value is between 0 to 1, right? So for 0 less than x less than 1, your fxx value is, it is the summation over y and fxy dy. We know that, right? How to extract the marginal mass density function from the joint density function, right? So integration over y. Now what is the y limit? Y limit is actually, because you have to think about this whole region. So we have already discussed how to find the y limit. So y is basically 0 to 1 minus x, right? Y value is between 0 to 1 minus x. And then fxy dy. Fxy value is what? 24xy into dy. And then if you calculate, then we'll get this value as, just if you do the integration, this is integration over x, so 24x can be outside into y square by 2, and limit is between 0 to 1 minus x. If we put the limit integration value, we will simplify it, we will get 12x into 1 minus x whole square. Done? So fxx is this one. Now you see that it is very much symmetrical about x and y, right? Whatever things, properties are for x, it is same for y. So can you not say what is fy of y? So fxx is this. Therefore, we can immediately say that fxx is this. Therefore, by the symmetry, we'll say that for 0 less than y less than 1, fy y of y is equal to the same 12y into 1 minus y whole square. Right? So therefore, the marginal density function we got, so we can easily calculate the expectation of x then. Expectation of x is, x value is between minus infinity to infinity. So x is minus infinity to infinity, but it is valid for 0 to 1. So instead of writing minus infinity to infinity, we'll do it at, it is 0 to 1, and then x into fx dx, which is 12x into 1 minus x square. And again, if we just simplify it, we can easily see that this value is 12 into this, after doing the integration, x square into 1 minus this. Nah? Okay, I'll do one more line. So 12 I'll take it out into 0 to 1 x square into 1 minus x square. So x square minus 2x cube minus plus x to the power 4 into dx. It is 12 into integration. After doing the integration, the root will be 1 by 3 minus 2 by 4 plus 1 by 5. And after simplifying, we'll be getting this value is actually 2 by 5. Right? Again, by the symmetry, we can easily say that u of y is what? The same value it should be. It is 2 by 5. And hence, covariance of x comma y is equal to e of xy minus ex into uy. So covariance was 2 by 15 minus 2 by 5 into 2 by 5, so 4 by 25. If you again simplify, we'll get this value minus 2 by 75. Right? So this is the covariance of this random variable, continuous random variable x and y. Done? So now we'll see some properties of continuous that covariance. So by definition, we can only say that covariance of x comma y is equal to covariance of y and x. We can easily prove it by the definition. Right? Again, covariance of x comma x is what? Covariance of x comma x is x minus ex whole square, but it is the definition of variance of x. Right? So the covariance of x comma x is equal to variance of x. So covariant between the same random variable, it is actually the variance of x. Then we can have this property. We can take covariance of ax comma y is equal to a into covariance of x and y for any constant a. Very easily one can prove it. And x plus c of y, if you do, it will not have any effect for c. We can easily see that this value is covariance of x can comma y. The proofs are written here. These are very easy to prove also. Then we have few more properties. The covariance of x plus y comma z, it is actually the bilinearity property. So it is covariance of x comma z plus covariance of y comma z. One can easily prove that one also like this. And if I generalize this concept, it is also true for like if I have the sum over this side. So after generalizing, one can also say that the covariance of I equal summation I equal to 1 to n xi comma j equal to 1 to m yj, it is their individual sum, covariance sum. And again, if we generalize this result, one can have a more generally way, one can also say just before we have one constant term ai and bj, we can say that this value is this one. So these are a few properties of the covariance. So all the proofs are written here. You may take the snap of it. You can just easily see that these are easily one can prove it. And then we have one two result, the variance of sum. The variance sum is what? It is the variance of I equal to 1 to n xi. Now we know that variance of x is equal to covariance of x comma x. So if I apply that property, it is I can write it in this way. And after doing some simplification, we can write and then write it in a different way. We can able to say that it is summation I equal to 1 to n variance of xi plus 2 into I less than j covariance of xi comma x. And if they are independent, then the covariance will be 0. So if x1, x2, xn are pairwise independent, we can say that variance of their sum is equal to their individual variance sum. Right? So this proof you can easily understand with the help of this small proof, that is the particular case. So variance of z equal to x plus y, it is covariance of z comma z by the property of covariance. And this one we can just do it with the again another property, and we can see that it is actually 2 into covariance of xy plus covariance x plus y. So we can easily write this one, and after we can also more generally we can write this. Right? So up to that I thought to discuss for this lecture. I hope you understood all the concept. These problems are not at all difficult. They may be little lengthy, but they are not difficult. So my suggestion is, please do solve few examples related to that so that you will learn more. Thank you very much. We'll meet in the next lecture.